Welcome everybody. So one last thing for this week is the development of these V alphas. We've been talking about these V alphas since the very first day of classes pretty much. And now we want to define them for all ordinals alpha. So here's essentially the definition by recursion. And this is for, let's write that down. And it's a definition that is going to work for all ordinals alpha. Let's go back to the intuition, which we did many times, but we might as well write it again. So the way you start, V0 is going to be the union of an empty set. So that's going to be the empty set itself. V1 is a set that contains the empty set. V2 is a set, it's the empty set and the empty set. V3 is a set, and so on and so forth. And then we had V omega, which was the union of all these guys. V omega plus 1, which was the power set of V omega. V omega plus 2 is the power set of the power set of V omega. Right, and that's what we get from that definition. You notice that this union up there, all these sets are included in each other. We always get this inclusion, which you can prove by finite induction, that you always get inclusion. And then when you take the power sets of a nested sequence, you still get a nested sequence. So they are all included in each other. So this is a chain of sets. So the union is just taking essentially the largest. If there is a last element, the union is just that element, the largest. If there is no last element, if you have kind of like a limit situation, like in the case of V omega, and we have to union all these guys, then we get kind of the supremum, the union of all these guys. That's the V omega. And then this is going to have another limit situation when you do V omega plus omega, which is the union of all the V omega plus n's, right? For n in omega. It's going to be a V omega plus omega, which is also going to be an infinite union. And these guys grow and grow and grow, right? And usually the picture one draws for, and this is where the V comes from. These guys, so here, down here we have V0. And here we have V1, and here you have V2, V3, and then you go on, and then you go on, and then you end up with a limit, and then you get V omega, which is all the ones below, and then V omega plus 1, and then you get to a limit, V omega plus omega, omega plus 1, omega plus 2, next limit, and then you get a limit of limits, and you get V omega times omega. It's a limit of infinitely many limits, and this picture keeps on going up. It looks like a V. That's why you get the V hierarchy of sets. Each one is a power set of the previous one, and starting from nothing, start building like that. And you get a lot of these sets. These are sets that are very special. We'll get into more about them in a minute. Okay, so this definition you can see by transfinite recursion. But and we're using just the union of the power sets of the range. So what we're doing here is nothing than the union of the power set of, let's call it A, for A that belongs to the range of V restricted to alpha, right? So this is essentially just something that depends on V up to alpha, right? Which is exactly what we have when we do transfinite recursion. Let's look for that slide. Here's a slide from a few videos ago, from last week I think, about transfinite recursion. So essentially you start with a well ordering, and you have this function gamma that is function-like, and actually and it satisfies even that for every x there exists a y such that this formula is true. So gamma kind of gives you like the graph of a function. And then you get that there is a unique function f, which in this case is a v function, the sequence of the v's, with domain A, in this case is the ordinal alpha, such that f of t is what you get when you apply this gamma to f at the previous values, right? So this is essentially kind of what we are doing here, right? So our function gamma is this one. That is the formula gamma. We have to spell that out in first order, but essentially that's what it is, where x here is essentially v restricted up to alpha, and this is V at alpha, right? So that's how you use transfinite induction to get these V's, except there is some little problem, which is we are defining this for all ordinals alpha, right? So if we look back at transfinite recursion, we have fixed a well-ordering A, and then we define this function on the well-ordering A. So essentially what we could do here is fix, let's say, a large ordinal, let's call it sigma, it's a large ordinal, and then if alpha is up here, we can define V alpha, right? So for each beta below, you can define this function V from sigma, I guess, well, with domain sigma, which satisfies this property, right? Transfinite induction allows us to define this function V up to any fixed sigma, right? But we need this is an ordinal, so it's a well-ordering, so it's a set. But now we want to define this V on all ordinals. For every ordinal alpha, we want to have a V. So this V is not really a function, the one that we want. Well, one thing that we had is that if you have this sigma as an ordinal, and then if we take another ordinal much larger, I don't know, tau is a larger ordinal, and inside we still have alpha and beta inside, we can define V alpha and V beta the same way, and we can now define it actually for all. Like if we have a gamma up there, we can define V gamma for that one up there using transfinite recursion. So we can go even further, and we are gonna get the same thing. This one is gonna be the same as that one. This is gonna be the same as that one, because of the uniqueness of that we get from transfinite induction, right? If you have this function and we truncate at sigma, this V up to sigma, that's the unique function that satisfies this transfinite recursion. So it should be the same if you look up to sigma or up to sigma as the initial segment of tau. You still get the same thing. So these two are the same. These two are the same. So we can always kind of, if we want to define V alpha some ordinal, we can always look at some larger ordinal and define V alpha up to all those ordinals up to the larger ordinal, including the one that you want. And by the uniqueness that we had a few classes ago, we get always the same value. Okay, so essentially we are getting a function, but again, V is not a function because we wanted to define for all ordinals, and we mentioned last week that there is no set of all ordinals, right? So we cannot have all ordinals in one set. So the domain of the function cannot be all ordinals. And actually, even like this week, a few videos ago, we show that there are ordinals that for every set, there's no set that dominates all ordinals, right? So you couldn't have all the ordinals in a single set. So this is another version of a stronger version of the Burali-Forti paradox. So okay, so we don't have. So the domain of this V is not a set because we wanted the domain to be all ordinals. So we're not going to treat V as a function. Okay, so this theorem up here, it's been up there for a bit now, it formalizes the way we want to treat this thing V. And this is what it says. There exists a formula, a first order formula in the language of set theory, such that for each ordinal alpha, there is a unique Y satisfying phi alpha Y. Okay, so essentially this is a formula. You can write down a formula, and it's function-like, and it works well whenever the first input is an ordinal. You always get a unique Y that satisfies the formula with this. And if we call this Y V alpha, it's a unique Y, so we can put it a name. For each alpha there is this unique Y, call it V alpha. Then we get, okay, so this formula phi is kind of defining uniquely your V alpha for each alpha, and it's going to satisfy the recursion definition that we want. So actually we're going to get the right thing. Okay, so these V's are not a function, but essentially for each alpha there is a unique one, so we can treat them like that. What is this formula? Phi alpha Y. What does it say? Well, it says this is this same thing that we kind of did up here. It says there is a, so the formula is true of alpha and y if there is a function f with a domain of f being equal to sigma for some ordinal sigma that is larger than alpha, so that contains alpha as a member, such that, and this function f, we wanted to satisfy this, that f of beta is equal to the union of the power set of f delta for delta less than beta for all beta in the domain, right? So we want f to satisfy this. So that means that f is going to be essentially the same as the v that we want, all the way up to sigma. And y equals f of alpha, right? So that's what the formula says, that there is a function that satisfies what v should satisfy, but not all the way for all ordinals because that's too much, but at least it does it up to some ordinal sigma, which is larger than alpha, that contains alpha as a member. And this function at alpha gives you what you want, the v alpha. Well, so you have to show this function is unique. It is a unique value. It doesn't matter what, if you go for a longer sigma, for a longer ordinal or a shorter ordinal, you're gonna get the same value for v alpha because of the transfinite recursion. They are defined exactly the same all the way up to alpha. It doesn't matter how far you go. So this is a unique y that you get here, independent of how far you go on which function you take. It's a unique function. It's a unique value of f of alpha. So that's what the formula says. Okay, so that's how we are going to interpret this v as a formula that says given alpha, this is v alpha. So it's not really a function itself, but almost like a function. Okay, so formally that's what it is. And we're gonna, so we have this picture, and then I guess so we are saying which sets belong to this picture, and we say that a set is grounded if it belongs to this picture. Okay, so the sets that are in here are called grounded. So if grounded, if you belong, there exists an alpha such that you belong to phi alpha. And then remember, this is still a first order formula, right? So this is saying that exists alpha. Alpha is an ordinal, meaning it's transitive, and the belongs relation is well ordered on alpha. And there exists y phi alpha y, and a belongs to y, right? Okay, so grounded means that you belong to v alpha for some alpha. Good. So these are going to be the nice sets. And if you're grounded, you must show up somewhere along the way on this v alpha. So we let the rank of A be this ordinal, which is the least alpha, such that you are a subset of v alpha. So in this picture up here, if you have a set A that is kind of elements all over there, there is going to be a first point here that you're completely contained on that one, and that's going to be the rank of the set, the first thing that completely contains you, right? So notice that that's v alpha plus 1 is the power set of v alpha, right? So that means that A is a subset of v alpha if and only if A belongs to v alpha plus 1, right? So actually, this is the same thing as saying you're the least alpha such that A belongs to v alpha plus 1. That would be the same definition, okay? So it's the first one that you belong to the next, okay? Exactly the ones that are grounded, the ones that belong to some v alpha are the same ones that are included in some v alpha, and the ones that have rank. So having a rank is the same thing as being grounded. One observation about these ranks that we're going to use later is that if A belongs to B, then the rank of A has to be strictly below the rank of B. So this tells you that the rank is kind of a measure of your size. It's not your size, but it's kind of your level in the hierarchy, kind of how late you appear in the hierarchy, which is how many nested you belong to are there inside you. Like is somebody inside a set that is inside a set that is inside is somewhere inside a set that is inside. How deep that nestedness goes. That's kind of what the rank is measuring. Why is this? Let's do a proof of this. Well, if A, so we know that B is a subset of V rank B, right? And we are assuming that A belongs to this set. And on the other hand, we know that rank of A is the least alpha such that A belongs to V alpha plus 1, right? So in particular, we know that rank of A plus 1 is going to be less than the rank of B because A belongs to the rank, to V of rank of B, right? So we get rank of A is below rank of B. So essentially, this is one of the main properties of this rank. It's a least function onto the ordinals that satisfies this property. Good. So this is gonna give us a way of painting, kind of imagining all sets that exist there in the universe of sets, in the V's. The obvious question now is: are there sets that don't belong to any of these V's, that they don't get built along the way at any point? And the answer to that is going to come next week when we introduce the foundation axiom or regularity axiom that says that essentially we have to actually add an axiom that essentially says that everything is grounded, everything belongs to one of these V's. Without that axiom, that's not necessarily the case. Okay, see you guys in the next video and we'll talk more about that.